Okay, so I want to show with a molecular model what it would look like to have an amino acid and what they look like in space, right, or in 3 dimensions. So as a start, I just wanted to show you again the methane molecule. So what we have here is a carbon atom right here in the middle, and then we have the 4 different hydrogen atoms around it, right? So if I spin it in space, I see that there are, it's a 3-dimensional object, right? We can see this with the methane CH4 molecule here. Now, when we look at the components of an amino acids, well, we know that there are, for one thing, we know that there is a carbon like this. So remember that there is a carbon that's called the alpha carbon, and then this alpha carbon has 4 links as we've seen. So we know that a carbon atom can interact with 4 different molecules or atoms at the same time. Okay, so we know that. So this is what we have here. We have this molecule here. Now, the other thing that we know when we're looking at an amino acid is that we have an amine functional group, right, or amino. And then if you look at this right here, we see that there is this little blue atom here. So that's a nitrogen. And then on that side here, we have both of our hydrogen atoms right there, right? So that's our NH2. And now if we look at the carboxylic acid part of that amino acid, we have the COOH, right? So C, and there is a double bond for that oxygen. So we have oxygen here in the red. We have our black ball here, which is a carbon, right? So we see there's a double bond right here, oxygen right there. And on the other side, we have CO, the O is right here, and then OH. OH is right here, right? So we have our oxygen here, and then the hydrogen atom at the end here. So now if I may assemble this molecule here from the simple components, now I have the central carbon here, which is my alpha carbon, and I will add to that carbon, I will add this amine group, and then on the other side, I will add this carboxylic acid to it, right? So here's what we have. So on that side here, we have the amine right there, and then on that side here, we have the carboxylic acid right here. Okay, so the other part that's important for the amino acid is that we have to our central carbon, we have a nitrogen right here, and then on the other side, and here's what I'm going to do here, I'm going to add this green little ball here. That usually is supposed to be a chlorine atom, but I'm just going to use this as our R, right? So the R, so we don't really know what that is right now. We don't need to define it at the moment, right? So this is our amino acid here. We have our central carbon right here. We have the carboxylic acid right here. We have the amine group right here, and we have the R group right there. Now, the reason why I want to show this to you right now is because this amino acid has interesting properties. This carbon part here has a link to other molecules, and what I want to show here is that it actually can move in space, right? So you see, it can twist and turn like that as we look at it, and because of that, when this amino acid is linked to another one, to another one, to another one, this will create a string, and that string will be able to move in space. So basically, it would create some kind of biological thread, and that thread can form different shapes, and that is very important. This is something I mentioned before. We know that structure, or the shape of things, is very important for the function of molecules, right? So if we have a specific shape to a molecule, it has a specific function. It does something specific. So That's one thing that is important here. This is what I wanted to show here. So remember that here, this has kind of like a lot of free range movement that we can see with a molecule like this one. So this next section, I want to talk about, get into the macromolecule world of amino acids and formation of proteins. And proteins, it's simple the way they assemble each other. So amino acid interact with one another and create a peptide bond, as we've seen. So if I may represent this peptide bond like this, so let's say that I have amino acid number 1, so I have 1 here, so that's amino acid number 1, and then we have a peptide bond that is created with another amino acid, and then we'll call this amino acid number 2. Please bear in mind that amino acid number 1, number 2 could be the same amino acid, right? 2 amino acids of the same kind can associate and form a peptide bond between the 2 of them. That's totally possible and it happens all the time. But then we can complicate things a little bit more now and then create this 3 peptide, and then we have 3 amino acid peptide, and then we add a 4th one, and then let's say we add a 5th one, and then we add a 6th one, right? So I could go like this all day and add one and the other, right? So the goal here is not to just draw strings of amino acids connected to one another. But what you need to remember is that between every single one of those amino acids, everywhere we have something that is called the peptide bond, right? Peptide bond, and we know that this peptide bond is created between the C side of an amino acid with the N side of the amino acid. So basically, the carboxyl group, or carboxylic acid group, to the amine group or amino group, right? So we know that we have a bond that would look like this. We would have something. So let me draw the peptide bond again. The peptide bond would be created between a carboxylic group. So like this, and then we have NH, and then we have the rest of the amino acid. That is our peptide bond right here. Okay? So the C side of the peptide, and then the N side of the peptide right here. Okay? So when that happens, when we have a string of amino acids that are connected with one another, we know that this string can be quite long. It can be thousands and thousands of different amino acids. Okay? So that's an important part. What I just showed you is that the central carbon can allows for some flexibility, right? So just imagine that my body right here, this is a central carbon, and on both sides here, I have the links, right? So I have my head is the first link to the carbon, the second one here, the third one, and then the trunk is linked to the other part, right? So we have my central carbon atom connected to 4 parts, other atoms, right? We know that a central atom here, so if I look at the links here, right, so if I position myself in front of the camera correctly, I can see that there is the possibility for some kind of flexibility right here. So if I look at the different peptide bonds between the different amino acids, it is now totally possible to imagine that we can have something that would look like that, right? We have some kind of a string of amino acids, one after the other here. I'm not going to draw all of them here, all united through a peptide bond. And we have these beads on a string like this. And this is flexible. It curves in space, right? Again, this is 2-dimensional. This is on a board, right? So I don't have the ability to show what's protruding outside or behind the board here. What I can do here is only the 2-dimensional side of that. But what I want to show here is that the links between every single amino acids within this string right here, that has a name. This is a structure, right? So this is a structure. All the amino acids are linked with one another. This has some kind of a structure, a beginning of a structure. And this here is called the primary structure. That's a primary structure. So the primary structure is the links between the different amino acids. And the links is a peptide bond, right? So what we have here is a long peptide. And this here is known to be the primary structure. So imagine a computer charging cord, right? A thread, a hose, whatever. In 2 dimension, we have this structure here that is known to be the primary structure. We know that proteins can have very complex structures. Now, I just mentioned the first stage of protein formation, which is the peptide bonds, the links between the different amino acids. This creates a primary structure. So if I ask you to name every single amino acid from start to end, so that from the C side to the N side of that long stretch of amino acid, you could name every single amino acid, right? It is possible to identify them. And if you told me, well, it's made of this one, this one, this one, and this one, then you would give me the structure, and you would give me the primary structure. So basically, it's some kind of a long phrase that is being written by different amino acids. Now, proteins have 3, even 4 different levels of organization, okay? So we have the first one, which is known as the primary, right? So we have primary structure, which is the beads on a string I just explained. And then we also have the secondary, and then tertiary, and then in the end, we have something called a quaternary. So you see different levels of organizations of proteins, right? So primary, secondary, tertiary, quaternary. This might look a bit complicated, but actually it's not really. It's just a level of organization, right? So if you think of Legos again, well, you build a house, you have this wall, right? And behind it, you have this wall, but then when you look from the top, you have all those rooms. And then when you go into rooms, you have maybe the furniture. And then when you look in the drawers, you have some folded t-shirts in there, right? So you see you have different levels of organization when you look at a big structure. Now, we've looked at the primary structure already. We've looked at that. Now I want to explain something that has to do with the secondary structure. Now you'll need to use a bit more imagination for this one, because when we looked at a primary structure, we looked at a 2-dimensional side to that. What we have is a board, and then we have that string like this, right? We have this string here. What I was very careful not to do is to show like intersections, right? So what I mean by that is I was very careful to show something like this rather than something where it crisscrosses, right? And there is a very big reason for this. Because if this is known as the primary structure, when we have something like this, this is no longer bidimensional. This no longer has only 2 dimensions. Because you see where it crosses here, it crosses maybe on top of what's behind, right? Just imagine like a thread that's folded on the floor, or a hose that's folded. Well, you know that the hose has a certain depth to it, right? You have the top, and then as you coil it down, it reaches the floor, right? So there's a top and down, not just like a surface. We have the width and the length of it. So what we have here is a bunch of thread that is going over and under. And this here, if this was two-dimensional, this here is three-dimensional. Unfortunately, I cannot show it here. I will show an animation that will demonstrate that, and I will include it in this video, but I just want you to know that here. So what we have here is primary, then here we have the secondary. Secondary is basically how the thread folds on itself. Now, you might think, well, this probably folds randomly, and you would be correct to say this, right? You wouldn't be totally correct, but you know, there's an element of truth to that. However, what we know is that in nature, things are very seldomly random. There's not much randomness to organization. Things tend to interact in a certain way because there are forces that forces them to interact in a certain way. Physical forces, chemical forces. I'm not talking about, you know, psychic forces or anything like that, right? I'm talking about very concrete forces, physical and chemical forces. And what I want to show here is that I want to show that some of the different organizational levels that a three-dimensional structure has, so the secondary structure. All right? So one way a thread could fold in space could be like a spiral, right? Just think of a spiral staircase, right? So you have some kind of a corkscrew motion to that. So you would have something that could go like this, right? On top, behind, top, behind, top, behind, top, behind, right? It coils in space like that. Well, when that happens, we say that this is known as an alpha helix. So alpha helix is a way that proteins can fold in 3 dimensions. We know that. There's another way it can do this, and it can form something else. So we could have something like this. So this looks 2-dimensional because it's on a board, but it can be bent, right? So just think, for example, a piece of paper, right? So I'm holding a piece of paper here and I can bend it in space, right? So this here is called a beta sheet. Beta sheet, right? So what holds these structures together? Well, what holds it together is very interesting. It's something we've seen before. And if I may do this by using another color, I will use red, right? And what I want to show is that there are interactions between amino acids that link these structures together. So you see there's some kind of a force that will act on the different amino acids here. And we have the same thing here. So we will have lots of different links that are connected here. Now, what's important here to know is that those are not, I'm not talking about covalent links here. I'm not talking about a real link between 2 atoms right here. Although that's possible, it does happen in proteins, but I'm talking about an interaction. And that interaction, we know what that is. We talked about that, but we talked about this in the context of water. But hey, guess what? It doesn't happen only in water. What we have here, in this case here, and in this case here, the red parts of that, that's hydrogen bonds. And we know that hydrogen bonds are not linked directly together. It's more an interaction between oxygen and hydrogen, right? Well, where's the oxygen coming from? Well, it's coming from the amino acids. We have carboxylic groups, right? We have a C and an O. This is part of that. This is part of the peptide bond, right? And where's the hydrogen coming from? Well, there's lots of hydrogen everywhere in our amino acids. So there is a possibility for these amino acids to interact with one another and form those shapes, 3-dimensional shapes, right? Secondary structures. Very important here. Now, I'm going to attempt to create a tertiary structure on a board like this. It won't be perfect. As I mentioned before, I'm going to include a little video and animation of a molecule spinning in space, like I've done with methane before. So I'll show you what that looks like. Don't worry, you have a good understanding, but I really want to explain something. It's quite simple, and it's not, it's not something that's very hard to understand. Now, here's a bit of nomenclature here. I want to show that whenever we have an alpha helix, we know what an alpha helix is. What I'm going to do now to draw this is I'm going to draw a box like that, right? So whenever you see a box like this, you know that in both cases I was talking about an alpha helix, right? So, and I'm just going to use this as an example to show what a tertiary structure is, okay? I just wanted to show that. So, and then when I want to talk about beta sheets, so beta sheets are like kind of like this, right? And they interact. Remember, there's an interaction here. What I'm going to do here is I'm going to draw an arrow. And I didn't make this up, so that will be for beta sheets, right? I didn't make this up. This is nomenclature. You'll see this in books over and over again when you see beta sheets on a surface or on a piece of paper. They don't usually show you this. They'll show you these structures right here, and then as the alpha helix will be like a box like that. So if you see an arrow, usually it is beta sheet, right? So what I'm going to do here is I'm going to remove all of this, and I'm going to create a structure, a protein that has a tertiary structure to it. So remember that there's a primary, secondary alpha helix and beta sheets, right? And then the tertiary is the interaction of all of those secondary structures with one another. So let's draw this. So what I will have here is I'll have a bunch of alpha helix somewhere in my protein, right? And then behind that, or around it, I could have something like this. So that let me just complicate things a tiny bit more. So in red, I'm now going to include a beta sheet right here. So you see, I'm being very careful to create it 3 dimensions. So stuff that are in front of things, and then sometimes they are behind as well, right? So I could have another beta sheet right here, but that beta sheet would be on the underneath that part right here. So let me draw this here. So I have a beta sheet here, and now let's just link all of these together. So my amino acids are connected. They form alpha helix right here. So remember, this is what we see here. They form the alpha helix. Not everything is connected through an alpha helix, right? So I would have these here. These alpha helix will be connected now to a beta sheet. That beta sheet could be connected to an alpha helix, and that alpha helix could now be connected to a beta sheet, right? So look at this mess, right? What we see here is a structure that started quite simple, the primary, that got complicated with alpha helix and beta sheets, and now we're using another element of that, and we are creating something super complex, because what we have here is an organization of those secondary structure. They get together, they clump together. And how do they clump together? Well, you know what? The same way the secondary structures do, via chemical and physical forces acting upon them. So what we see here is a 3-dimensional structure of a protein, a polypeptide, right? Many peptide bonds. So polypeptide that's folded in a way like this. These parts here that interact with one another, that has a name. And these are called domains. Domains. And by the way, all of this vocabulary, it's important. Not because it could be on an exam and then I'm going to ask you what a domain is, the definition. It's not for that only reason. Most importantly, it's because now that you're studying biology, you will be, you're now aware of the vocabulary that is used in science of biology and chemistry. And you need to know that. So if you ever read something about a protein, it has this domain and this domain. Well, you need to know, well, what is a domain? Well, a domain is this. So what is a domain? The domain is this part here. These parts that interact with one another. And proteins might have more than one domain. You might have a domain right here, but you might have another domain here because those two alpha helices are interacting with one another. So you would have domain number 1 right here, and then you could have a domain number 2 right at this spot right here, right? So proteins can be multi-domain. That's what I wanted to show here. What I want to talk about now is the last level of organizations of proteins. So primary, secondary, tertiary. The one missing now is quaternary. So let's just imagine that our structure that I've drawn, right? So that multi-domain structure here with different alpha helices, and then we have beta sheets and all of that, right? So this is kind of a messy organization here. Let's say that what I'm going to show now is like basically a little ball, right? So when what I want you to see is that instead of having this huge mess on the board, I will represent what I just drew via a little, ball like this. So what we have here is a bunch of proteins and they're folded together. Now, the quaternary structure is when different subunit, and that is now called a subunit right here. So let's call this subunit number 1. And then I have another one here. Let's say I call this a subunit number 2. And let's say that this subunit number 2 has a bit of a different shape to it. Now we know why. There can be different shapes, right? So I have subunit number 2 here. And then let's say that I have another one. I have a subunit number 3 right here. So I have 3 subunits, right? I have 1, 2, and 3. Each of them having a primary, secondary, tertiary structure. We don't know this. We don't need to draw it right here. This is not important. What I want to show, though, is that when we're talking about the quaternary structure, I need a bit of space here to explain this more. So I want to talk about the quaternary structure. So when I want to talk about quaternary structure, I will look at those subunits, and I will look at the way they interact with one another, right? And they might interact in 3 dimensions as well, right? So here's what we have here. So we have our subunit number 1 right here. We have our subunit number 2 right there. And then we have here, we have our subunit number 3. So subunit number 2, you see it's right here, right? And it's in front of subunit number 1 and in front of subunit number 3. So basically what we see here is, once again, an organization of structure, 3 dimension. Now, what we see here, I oversimplified everything because we can't now draw precisely where all the amino acids are and everything. But please remember, bear in mind that this is highly complex now. We have a very high level of organization. Now, what we have here is the subunits. They're not necessarily connected in the primary structure. Now, let this sink in for 2 seconds, okay? A subunit, if I draw only the primary structure, I could have something like this. And then for subunit number 2, I could have something like this. And then for subunit number 3, I could have something like that, right? So those are all the primary. You see, they're not connected with one another. There's no peptide bond between them. So the subunits can indeed interact with one another by being their own thing, but they might interact via different chemical and physical forces, linking them together, not necessarily through a covalent bond. Having said that, it is possible that to create peptide bonds or other types of covalent bonds that will hold those structures together, but they don't have to be. Okay? The hemoglobin that is flowing through your veins right now, as you're scratching your head thinking, what did I get into here? The hemoglobin has 4 subunits, connected with one another. So your hemoglobin has a quaternary structure, and that quaternary structure is super important for the function. Remember, there's a shape and there's a function, and the two of them are connected together. Well, that's a direct result of the quaternary structure, the tertiary structure, the secondary structure, and the primary structure. Okay, so that is a very important piece to understand the formation and how proteins are made.